run. Let's talk about a classical matrix multiplication algorithm, so not Russell-like or arithmetic progression routines. In terms of its theoretical complexity, there were many past works in the subject in the 20th century. However, there is still something to add in this topic. In this work, we have proven tight, sequential and parallel I/O lower bounds, up to a small additive factor. And not only our algorithm achieves it for all combinations of parameters, but also in practice it outperforms best available BLAS libraries in all scenarios. So let's see how to do it. I guess I should start with a motivation here, but probably will agree that in HPC, no matter what you compute or how you compute, you're likely to end up multiplying some matrices. Nevertheless, please let me show you two use cases that I find somehow extreme in this case. So first would be molecular simulations. So here to simulate only 64 water molecules bonds with enough precision, it's called fifth rank of DFT, one needs to multiply matrices of sizes 17,000 times almost 4 million. So those are huge, tall and skinny matrices. The other side of the spectrum would be, for example, these positive quantum transport simulations. So here to simulate, among others, heat dissipation in modern FIFO transistors, the algorithm multiplies very small matrices, just 12 by 12. But to do so, one needs to multiply them more than 100 billion times. To get a decent performance, the matrices are strided and combined to form again these tall and skinny matrices, but still very small. And this kernel alone can take more than 70% of the total runtime. Okay, so on one hand we have these matrix problems, on the other we have these huge distributed systems with tens of thousands of cores, with tens of thousands of nodes and millions of cores. So how to efficiently multiply these matrices on these systems? Well, let me take you on a brief tour to the world of matrix multiplication algorithms. So on a y-axis we'll have the worst case I/O cost. So for some combination of parameters, some algorithms can perform really bad. And on the x-axis we have time. So back in the old days, huge matrices were usually multiplied just row by row. So this is what we would call a 1D decomposition. Now the first optimization you can do is decompose both matrices, and this is what Canons did in '69, and this formed the basis of the 2D decomposition family. Meanwhile, the first asymptotic sequential lower bound was proven by Hong and Kung. Now the problem with Canons algorithm is that it works only for square matrices. So first it was extended to handle rectangular ones, and then with enhanced communication pattern and data layout decomposition, it formed the basis for SUMA algorithm. Actually, in the same time, the first 3D algorithm was proposed by Agarwal et al. However, this particular implementation had some performance issues and it was not widely used afterwards. Nevertheless, it formed the basis for the 3D decomposition family. So the algorithm does also parallelizes in the reduction dimension. Okay, meanwhile, in the lower bound business, the first parallel I/O lower bound was proven by Irony et al. However, this lower bound is not tight. Okay, so the first algorithm that efficiently interpolated between 2D and 3D and used the excess memory was the so-called 2.5D algorithm by Solomonic and Demel. But it had some performance issues with non-square matrices, and to handle this problem, the recursive CARMA algorithm was proposed, which is asymptotically optimal for all matrix shapes. However, again, it is not tight. Now, 2 years ago, the first tight sequential lower bound was proven by Smith and Van den Rijn, and well, here today in 2019, the first tight, we've proven in this work, tight parallel I/O lower bound, and our COSMA algorithm, which achieves it for all combinations of number of processors, memory sizes, and matrix shapes. So, what is the difference between COSMA and other decomposition algorithms? Well, the high-level picture is that if we multiply two matrices, A and B, to get C, then one, the decomposition would parallelize, for example, just by rows, then 2D decomposition would parallelize both rows and columns to get this rectangular grid, and 3D decomposition would parallelize rows, columns, and also in this reduction dimension, introducing the communication between the ranks in the reduction. So this is what we call a top-down approach. So we look at the global problem, the global matrices, we look at how many ranks we have, and we keep on cutting the global domain until we have the number of subsets equal to the number of ranks. COSMA, on the other hand, takes a different approach. So it aims to optimally use local resources. So from the perspective of a single sequential processor, what is the most efficient use to maximize the reuse of its own local memory? So having, for example, cache size of size S, we form this optimal square tile. We look at the input dependencies. This will be this one row of A and one column of A and one row of B. And then we accumulate this outer product inside this fast memory, maximizing the reuse. So this is a well-known outer product tiling formulation. Now, to get from the sequential optimal schedule to the distributed one, we extended this outer product to the whole global domain. We examine where is the data reuse. So here we don't want to parallelize because that would introduce communication. So we would assign, in this example, all the reductions to one rank 0, maximizing the reuse, and then independently, these outer products would be assigned to rank 1, rank 2, and rank 3. So this is how the bottom-up distributed decomposition would look like. So what we can see is that the local domain per rank here is this optimal square shape which maximizes the reuse compared to this stretched rectangle in the top down, and also the communication in the reduction dimension between ranks is minimized. Okay, so this is the high level picture. Now in this work we really wanted to prove that this is really optimal and derive all the constant terms. So to do so we need to do a bit of maths. And let's jump to the I/O complexity theory. We'll start with a Red Blue Pebble game abstraction. So this is a Pebble game played on a computational DAC. So here every vertex is some intermediate computation, and edges represent data dependencies. So we have some input vertices, we have some output vertices, we have some red pebbles. So here we have 5 red pebbles. So these ones correspond to our fast memory, for example, registers or cache, in which we can perform computation. And we have infinite number of blue pebbles, which correspond to our slow memory. We start again by putting blue pebbles on our input vertices, and then we keep on playing the pebbles according to certain rules. For example, putting a red pebble on a blue one is a load operation. We load something from the slow memory to the fast memory. We do another load, another load. Now we do a computation. This is another computation. This is another computation. Now putting a blue pebble on a red one is a store operation. And we keep on playing these moves until all the outputs are computed. So all the output vertices have blue pebbles. So this may be, for example, a final configuration of the game. Now it was proven that it is p-space complete to find the optimal sequence of the pebbling moves. So instead, to get some feasible solution, the original observation was to examine just a small subset of vertices. So then we asked ourselves a question: what is the minimum number of I/O operations required to pebble, so to compute this subset? Now what we can see is that we have 8 inputs, this is called a dominator set. We have 8 outputs, this is called a minimum set. And now the original observation was that if the sizes of these sets are 2s, so here if s in this example would be 4, then the sizes are 8 here, then what happens? Then having these 4 red pebbles, at most 4 of them can be reused from the previous computation, so they can be already placed beforehand in a dominator set. So it means that the remaining 4 have to have blue pebbles. So at some point we'll be putting a red pebble on a blue one, so these vertices correspond to our load lower bounds. We'll have to put at least 4 loads, and the same argument goes for stores. Now, knowing that, all we need to do is basically count how many of such subsets we need to cover the entire CDAC. So in this case it will be maybe 7, 8 subsets, and this forms our I/O lower bound. So here S is 4, and this is this minimal I/O per subset, and then the number of subsets in this partition. Okay, so this is a valid I/O lower bound, but this actually may not be tight, and in our work we really wanted to push this bound as high as possible to get a tight I/O lower bound. So we extended the 2S partition to the X partition abstraction. Now what happens here is that if we can prove mathematically where exactly are all the red pebbles, for example, if we can prove that this red pebble has to be there because of some reasons, then what happens? Then we are left with only 3 red pebbles that can be reused from the previous computation, being in a dominator set. So it means that the remaining 5 vertices have to have blue pebbles. So it means that we'll have to perform at least 5, not 4 loads operations, because the reused red pebbles, we have only 3 of them here. So this is the main result in this section of our work, our X partition lower bound lemma, where X, the dominator set size, can be of any size. It can be 2S, as in the original work, but also it can be larger or smaller than 2S. And then for particular value of X, we find what is the maximum reuse. For example, in that case, in the previous example, this maximum reuse was just 3 red pebbles. The same argument goes for stores, and then the numbers of subsets in X partition. Now, to prove this lemma, actually it required quite a bit of work with several intermediate steps, but in the end it gave us a very powerful tool, because X partition works for any computational DAG, and it allows to drive the lower bounds much higher. So, armed with our new powerful tool, let's tackle matrix multiplication. So we need to start by finding matrix multiplication CDAG. So it is often interpreted as this 3D iteration space. So for example, multiplying matrices 2 by 2 times 2 by 3, we need to perform 12 multiplications. Now looking at the data dependencies, for example, for this result of multiplication, we need these inputs from matrices A and B, and also the previous result from the reduction from the matrix C. Now looking again at remaining vertices, we form the data dependencies forming these edges, and this is how our matrix multiplication CDAC looks like. Great, so let's now tackle it with our X partition abstraction. So we'll ask ourselves a question: what is the minimum number of I/O operations required to pebble, so to compute this subset? As a first step, we need to form our dominator set. The dominator set for this particular subset will be formed from these vertices of matrix B, this vertex from matrix A, and these ones from the previous computation in the reduction. Now remember that we need to find the optimal value of X, and where exactly are all the red pebbles, and which vertices have blue pebbles. To do so, actually, it required quite a lot of steps, and unfortunately we don't have time to go through all the details, but if you're interested you can find them in the paper. But at the end, we have proven that the I/O is minimized when all the red pebbles are placed in the vertices from the previous computation in matrix C, and then we have square root of blue pebbles in matrix A and square root of S blue pebbles in matrix B. Now, what happens is that we move all S red pebbles upwards and compute S new values in this 3D iteration space. Okay, so this is a single I/O optimal subcomputation. Now, how to get to the distributed setting? Well, to get to the distributed setting, we take our I/O optimal subcomputation, we extend it to the whole global domain. We know that the I/O is minimized if all the red pebbles are moving only upwards. So we know that each of these pillars is independent because red pebbles don't move horizontally here. So now what we can do is assign each of these, in this case, 6 pillars to a different processor. So for up to 6 processors, we just have this 2D decomposition of assigning independent pillars to each of the ranks, and we'll have to just load these 2 faces and store the final results on the top. So this is how the decomposition for p equals 6 would look like. Now if we add more ranks, then we have to cut in the k dimension, like that. So this is how the decomposition for 12 ranks would look like. And now if we add more and more ranks, then we keep on cutting in the k dimension until the local domain is this cube of sizes square root of s, square root of s, square root of s. Now if we still insist on adding more and more ranks, then what happens? Then the local domain will still have to remain a cube, and then we will just shrink all the dimensions of this cube. So for example, for 54 ranks, this is how the decomposition would look like. So again, this is the intuition. Now of course we need to prove that this is really I/O minimizing decomposition. So we have to proceed to several steps, but this is the high-level intuition how the proof goes, and this is how we obtained our tight parallel I/O lower bound. Okay, so this ends up our theory part. Now, to get a decent performance, of course, we needed to introduce several optimizations. For example, we have the full communication computation overlap. We have both one-sided and two-sided asynchronous MPI implementations. Thanks to static analysis, we allocate statically minimal-sized buffers, and thanks to the memory pool management, we maximally reuse them between the communication steps, and we introduce what we call the processor grid optimizations. Now, due to the time constraints, I will just focus on the last part. The remaining ones you can find in the paper. So, what is this processor grid optimization? Now, if the number of ranks we have is difficult to decompose, for example, we have here in this example 65 ranks, which is 5 times 13, then to use all the resources, we will end up with this really communication suboptimal grid to the left, which really increases the communication. But if we are willing to drop just a single rank here, then we can have this communication optimal cubic grid to the right. So in this case, by dropping a single rank, we will increase the load by just 1.5%, but we will reduce the communication by 36%. So we designed a heuristic that guides us how many ranks it is beneficial to drop to decrease the communication volume. Okay, so we compared COSMA against Intel ScaLAPACK library, CTF, and recursive CARMA algorithm. As a first step, we examined the theoretical complexity of these decomposition algorithms, and what we found out is that the 2D decomposition is just not optimal. 2.5D may be I/O optimal for square cases, but it has some penalty for tall and skinny ones. Now, recursive CARMA algorithm is asymptotically optimal, but this factor square root of 3 is not tight. And then we have COSMA, which is optimal in all cases. And now let's see how COSMA works in practice.
Alright, so let's see how COSMA works in practice. We performed the benchmarks on Piz Daint supercomputer, which is number 6 in top 500 list. We tested different matrix shapes and also different scaling experiments. So we have strong scaling and we have two versions of weak scaling, namely weak scaling when we have just enough memory and also weak scaling when we have a lot of extra memory. We measured the total communication volume per rank and also the speedup. The speedup is the ratio of times that COSMA needs to perform the multiplication versus the second best. Regarding the communication volume, COSMA was always communicating the least amount of data compared to all the others. CARMA was sometimes close to it, but still most of the time COSMA was communicating far less than others. Regarding the speedup, COSMA was always the fastest one, and the closest that some other algorithm approached the performance of COSMA was in the easy to decompose square case, in which case the second best was CTF. However, in more complicated cases, when we have two large dimensions, COSMA achieved a speedup of almost 13 times, and the second best in this case was ScaLAPACK. Here we can see the total communication volume for each of the three scaling experiments for different number of cores. So in this case, lower is better because we want to minimize the communication volume. COSMA is shown in green, and we can really see that COSMA achieves the lowest communication volume in all the experiments. And we also measured the percentage of the peak performance. So in this plot, higher is better because we want to maximize the throughput. Again, COSMA is shown in green, and COSMA really achieves the highest throughput compared to all the others, and sometimes even achieving up to 90% of the peak performance. Now, these two plots were for the large K shape of the matrices, but a similar thing can be observed also for other shapes of the matrices. Now, one might wonder what the relation is between minimizing the communication volume and maximizing the performance, so maximizing the throughput. For this reason, we looked at the breakdown of time for COSMA, and here in light blue, you can see how much time is spent in computation for COSMA, right? For different shapes of the matrices. And the bottom part actually shows how much time is spent in communication. We can see that it's only up to 30% of time that is spent in communication. Now, we might wonder if it really makes sense to minimize communication, which only takes up to 30% of time. However, you have to keep in mind that COSMA is already communication optimal. And in fact, if COSMA was communicating as much as the second best in this case, it would actually increase the runtime by 60%. And in this case, it would actually increase the runtime by more than a factor of 2. So even if the problem itself is compute bound, is computation dominant, it still makes sense to minimize the communication volume. Now, lately, we've been also working a lot on the portability and usability of our code. So let's say that you have your own code and you want to use COSMA. Now, what can you do, right? Well, maybe your code already uses ScaLAPACK layout. So by layout, here we mean the way how your matrices are distributed and also the API. So if your code is already using ScaLAPACK, you can just link to COSMA because COSMA actually supports ScaLAPACK API. So in this case, you don't have to change your code at all. It will automatically use COSMA in the background. And by the way, our ScaLAPACK layout also supports a Fortran interface for the hardcore users. Now, maybe you want to adapt your code to use the COSMA layout, in which case you will get the maximum performance. And maybe you have your own custom layout. So you have your own way how your matrices are distributed among the ranks. And in that case, COSMA can adapt to your own layout. Regarding the backends, COSMA is GPU accelerated, and our GPU backend supports both NVIDIA and AMD GPUs. Now let's see how the GPU backend works. Our GPU backend is called TiledMM, and it is a simple tiling algorithm. So tile by tile is sent to GPU, computation is being performed, and the result is sent back to the CPU. Now, here there are two things we should keep in mind. First thing is that we really want to copy C only once. So we want to copy the result back from GPU only once. We want to reuse as much data on GPU as possible. And the second important thing to keep in mind is that if you focus on this part and we enlarge it, we actually can see that it's always better to send tiles of A and B together and never to interleave them as shown below, because if we interleave them, it might actually introduce some delay in the kernel execution, which is definitely something we don't want. Now, with these two things in mind, we actually managed to outperform the NVIDIA cuBLAS XT by up to 30%. So in this plot, we actually show the throughput, and we Dialem almost achieves the peak throughput of the node. And our library, so this GPU backend, is available as a standalone library, and it's completely free. Now, another interesting thing is the custom layout. So let's see how it works. Maybe your matrix is distributed as shown on the left. Well, but maybe in this case, Kozma assumes a different distribution as shown in the middle. Now, what can we do in this case? Well, we can either let all the ranks communicate, so do all-to-all communication and exchange all the pieces, or we can be a bit smarter and we can actually relabel the ranks to minimize the communication cost. What this means is that in this case, we would relabel rank P1 to actually be P0, and we can do a similar thing for other ranks. In this case, we actually achieved the targeted layout, but with performing zero communication. And in fact, Kozma will do a similar thing for any custom layout if it actually represents the data reshuffling problem with a bipartite graph, where each edge represents the communication that would have to be performed in order to change the layouts. Now, in this bipartite graph, Kozma will actually find the maximum weighted perfect matching, which would give us the optimal relabeling. So the relabeling, which minimizes the communication for data reshuffling. And at the end, we want to see Kozma in action. So what we want to compare is, we want to compare Kozma, but now using ScaLAPACK layout versus ScaLAPACK itself. So we took the case where ScaLAPACK really shines, which is the square matrices case, where all the block sizes are square as well, and where the processor grids is also square. So in this case, ScaLAPACK only has to multiply, whereas Kozma has to create communicators, allocate memory, solve perfect matching, transpose, multiply, and free up all the memory. Now, you will really agree that in this case, so that this scenario really favors ScaLAPACK. However, our benchmarks actually show that Kozma outperforms ScaLAPACK on both CPU and GPU. So on CPU, it's up to 2 times faster, and on GPU, it's more than 2.5 times faster, even with ScaLAPACK layout.
Okay, so to sum up, COSMA, communication optimal S-partition-based matrix multiplication algorithm. So in this work, we have shown the X-partition abstraction, which can derive the tight lower bounds for any computational DAG. Then we use this abstraction to derive tight sequential and parallel I/O lower bounds for matrix multiplication. We showed that in practice, COSMA communicates the least and is the fastest in all scenarios. And finally, COSMA is open source on GitHub and is SPAC installable, so you can get your COSMA GPU accelerated COSMA today and transparently use it with your ScaLAPACK application. Thank you very much for your attention.